All right, so as you enjoy the lunch, let me briefly introduce our distinguished speaker today. It's Professor Bhushan Gopaluni from University of British Columbia. As you may know, UBC is one of the top institutions in Canada, and we are very honored to have Professor Gopaluni here. So he's a professor of chemical and biological engineering in UBC, and also holds the title as the Vice Provost and Associate Vice President of the institution, which is certainly a very high-level ranking order. Dr. Gopaluni received his bachelor's degree from IIT Madras and a PhD degree from University of Alberta. After a short career in industry, he joined the faculty of University of British Columbia and has been there for, I guess, 20 years so far?
18.
18, close enough.
Close enough, yeah. Thank you. Good approximation.
And he was really, a leader in the field of AI in general, but broadly focused on manufacturing, process industry, etc. He has received many honors and awards. I'm not going to read all of them, but just want to point out that he is also elected as a fellow of Canadian Academy of Engineering. So that's pretty much equivalent to U.S. National Academy of Engineering, the highest honor that an engineer can receive in the country. So please join me to welcome Bhushan to Cornell.
All right, thank you very much for that kind introduction, Feng-Chi. Looking at the title, if you're wondering you're in the right room or not, please don't worry, you're in the right room. I'm going to jump into switch gears in just a moment and jump into the presentation, the topic for today. So good morning, everyone. Happy Good Friday. My family was not really happy that I was going to be here on a long weekend. Good Friday is a holiday in Canada. But I'm really pleased to be here, honored to be hosted by Professor Feng-Chi Yu. I also want to thank Benjamin, Apur, and Gurpreet, and others who have helped us behind the scenes to make this presentation happen. So yesterday, I flew into New York, and then I took another flight here. I was really horrified by the traffic there. I almost missed my flight into Ithaca. I was very happy to land here and not see big crowds in such a beautiful campus. It was very pleasant to not have that kind of traffic here. And I think you're all really lucky to be studying here. What I want to do today, before I jump into reinforcement learning, is talk to you a little bit about some of the work that happens in my research lab. In the last 10 years or so, we've seen major strides in artificial intelligence and machine learning and their applications in a wide range of areas, primarily in computer science, but we are seeing applications of those same ideas in systems and control and in chemical engineering and process systems engineering. And I think it's because of serendipitous confluence of four things. We have Internet of Things, meaning every piece of equipment, every device is connected to internet. We are collecting massive volumes of data. We have all these sensors that are generating massive volumes of data. And in fact, I think most industries are sitting on treasure troves of data without fully utilizing their value, right? Internet of Things, lots of devices that are generating lots of data. In addition to that, we also have enormous computing power that did not exist just a few years ago. And lastly, we've seen in the last 10 years or so major strides in machine learning algorithms. Just in the last 10 years, deep learning was introduced in 2011, about 14 years ago now. But since then, we've seen major strides in machine learning and artificial intelligence. And I think it's the confluence of these four things: sensors, data, computing power, and algorithms that has created a lot of optimism within process systems engineering that we can bring a new level of automation to the industries that we work in systems and control and related areas. So in my group, our focus is on building the self-driving industrial processes that include cloud onboard AI-enabled intelligence, self-diagnosing, self-maintaining assets, virtual assistants, virtual reality-enabled control rooms, all of this while guaranteeing optimal performance, safety, and reliability. Right? How do we get there? It's not an easy task. Most industries are already very highly automated, but I think the new tools that are available to us in machine learning and artificial intelligence will enable us to take the level of automation to a much higher level. In 2019, there was a really nice paper published by Alf Isaacson in Journal of Process Control on different levels of automation that are possible in the industries. With the new tools that we have, And by putting all of these things together, I believe a new much higher level of automation can be achieved in the process industries. Now, in order to do that, you have to put together different pieces, and that's where we focus our research on. And I want to talk a little bit about some of the applications that we engage in often, and then I'll talk about the major areas. After that, we'll shift gears and jump into reinforcement learning. Canada, as you might know, is a really large country. And in terms of land, it's probably larger than the United States, but we don't have the same population. Canada has only about 40 million people, approximately. And it is natural resource intensive, meaning the industries in Canada are mostly in the natural resource sector, and naturally a lot of us at universities in Canada in chemical engineering work with a variety of industries in the natural resource sector that include forest bioproducts. That's a paper machine. You're seeing in the video, you're seeing the end of a paper machine. Some of you may not know this, but paper is made at speeds of about 120 kilometers per hour. If you have any questions as I go through this, or just want to engage in a conversation, please feel free to pause me. That should be fine. We work with mining industry quite a bit. We work with oil and gas industries. We also have a very strong biotechnology and pharmaceutical industries. So these are some industries that my research group works in. More recently, we've been working on smart building, space, and energy management. For many years, we've also looked at advanced battery management systems, especially state of health and state of charge estimation. More recently, we've been looking at accelerated material discovery for carbon capture and storage. We also work on health analytics. For instance, we have a project right now where we are using sensors on patients in emergency departments, collecting a lot of data on their health, heart rate, oxygen levels, blood pressure, etc. Putting it in the cloud and using that information to triage patients more effectively, more efficiently in healthcare settings. For instance, Canada has a population of 40 million people, and apparently there are approximately 30 million visits to emergency departments every year, and the average wait time is about 7 hours or so. So what we're trying to do is use this data from the patients, put it in the cloud, and process it using machine learning tools to triage patients more effectively, and then process them through these emergency departments much faster. All right. So those are the application areas, and you're probably wondering what's the common thread that's connecting all of these areas, right? In all of those areas, except perhaps in biotechnology and pharmaceuticals, we generate enormous volumes of data. There's a lot of data, and often this data are heterogeneous in that you have time series data, categorical data, images, text, videos, etc. In the past, in process industries, we used to focus primarily on time series data. We've been doing artificial intelligence in the process industries for maybe 3-4 decades. Some of my senior colleagues would certainly argue that. But we've rarely used heterogeneous data. With the tools that we have today, we can use heterogeneous data to solve problems. So that's one common thread or common characteristic across different applications that I showed you earlier. They also are determined by underlying complex nonlinear dynamics that we don't fully understand in many cases. In other words, there's a lot of uncertainty associated with those systems. There's a lot of noise, stochasticity. So in light of all of these characteristic features that are common across the applications that I showed you, how are we going to solve problems, generate actionable insights? In my research lab, we work in 4 different areas. I am a firm believer of using data visualization even before you use any machine learning tools in order to extract the most possible information out of data. And oftentimes you'll be surprised, just by visualizing your data in the right way, you will be able to extract a lot of insights from your data. What you see on the left-hand side is data visualization. I have some projects on data visualization. The picture over there is an infrared image of a lime kiln. Lime kilns are really massive. They apparently generate, the one that we worked with generates greenhouse gases that are equivalent to 300,000 cars running on the roads for one entire year. So we used infrared cameras to stitch together those images to help operators and engineers identify what are called rings in these line codes. Okay, so this is one very simple way of visualizing data. We published a paper a couple of years ago in Control Engineering Practice where we came up with an approach to visualize model predictive controllers. Okay. We also work on building large-scale models. There are lots of systems out there, interconnected systems that are not easy to model, but they generate a lot of data. So we use a wide range of tools to build large-scale models or digital twins. We're also interested in performing postmortem analysis on data, historical data. That's called fault detection and diagnosis. In addition to that, we use models to predict impending abnormal situations or faults. Okay, so that's another area: predictive analytics, fault detection, and diagnosis. The spiral graph that you see here was prepared by one of my students. This picture here is that of an electric furnace. It's a large electric furnace in a mining plant. The electric furnace has two electrodes. At the bottom of these electrodes, there's an electric arc that completes the circuit. The electrodes are used to melt ore. Every once in a while, they lose the electric arc at the bottom of that electrode, and when they lose the electric arc, they have to restart the furnace. That takes about 15 to 20 minutes. In a year, they have about 800 to 900 such events, which means they lose effectively 2 weeks of production time because of this loss in electric arc. What we did was we built a wide range of models to allow engineers to predict a loss in electric arc 5 minutes early with 75% probability. Right? So that's one example of how models can be used for predictive analytics. And finally, we are also interested in taking optimal decisions under uncertainty. You don't know what the future holds. There are lots of things that can go wrong, or lots of things that can change in the future, but you are generally required to take a decision right now to influence what might happen in the future. And that is optimization and control. There are many different ways to do this. And today, what I'm going to do is talk about reinforcement learning. Reinforcement learning is an approach to take optimal decisions in light of uncertainty. Okay. This is a pilot scale facility at Honeywell that we use to design these controllers and implement them. I'm going to talk more about this picture as we move forward with the slides. Are there any questions? Anything? Please, let's make it engaging. You can just ask me anything. Anything, even things that are not here. Right? All right. So that takes me to the topic of today's presentation: stable and sample efficient reinforcement learning. How many of you are familiar with feedback control? I would assume everybody, right? Okay, so I'm seeing mostly people nodding their heads, but let's just quickly go through this, just in case you're new to Cornell or new to the systems engineering program. This is a standard feedback loop. We don't use open loop because if you use open loop, you have to pre-plan your actions. It's relatively simple, but errors often tend to compound, meaning you won't be able to track your input signal, right? On the other hand, if you have a closed loop system, then you can dynamically correct errors. Closed loop systems are robust, and they can also be stabilizing. Okay. But the problem is, typical process industries have hundreds of these loops, hundreds of controls, hundreds of closed loops. If you have one control loop, it's manageable. You can identify a model, you can synthesize a controller, and validate it, right? But what if you have hundreds of control loops? That calls for a new paradigm. Is there a way to automatically scale your controller and tune all of them at the same time? There are, of course, controllers, multivariable controllers like model predictive controllers, but I'll tell you why tuning them is not straightforward. In fact, a few years ago, I think when I was doing my PhD, an engineer working at an oil refinery told me that a vast majority of their controllers are actually not tuned because they just use default settings. Default settings in these control loops are robust. They give you robust performance, but they give you robustness, but they don't give you the performance. And often, because of lack of time and the effort involved in tuning control loops, engineers tend to use default settings. What it means is you have a stable process, but you're not extracting the best out of your controllers. So the question that we wanted to ask was, how can we scale these control algorithms? Is there a way to go from process data to the controller directly without having to go through those steps, model identification, synthesis of a controller, and validation? Okay. So I think in 2018, when deep learning was taking off, there was a lot of interest in deep learning. I went to Honeywell. We've had a very long collaboration with Honeywell in North Vancouver. So I went to them and I told them, look, there's this new algorithm, deep neural networks, and we can combine them with reinforcement learning and replace all your control systems, right? So they have existing hardware and software infrastructure that they've been using for many, many decades. So I went to them and I proposed this framework to them. So you have some system. I'm going to replace your controller or approximate it with a deep neural network, and then add a reinforcement learning agent on top of it, right? You might ask, why do you want to do that? The current state of art is depicted in this picture here. You have a system, there is a controller, either a PID controller or a model predictive controller, and those controllers need to be maintained. If you don't maintain them, you're going to lose the performance from those controllers. So for instance, once somebody from a refinery showed me a very interesting graph. On the x-axis, you have time. On the y-axis, the performance of a model predictive controller. Typically, model predictive controllers, it takes to design and commission them on a large-scale process, it takes about 2 weeks for a few engineers to design and commission it, right? And then you start reaping the benefits of having installed a large-scale model predictive controller. Those benefits will probably last for a few months. And if you don't maintain the controller, if you don't remodel, retune your controller, you're going to start losing the benefits of having commissioned an expensive model predictive controller. Or for that matter, even a simple PID loop. Then consultants and engineers will have to step in and retune their controllers to bring them back up to the performance that you were achieving when they were first installed, right? So that's the current state of art in most cases, right? So in order to replace that, we proposed this one, and Honeywell, my friends at Honeywell immediately said, no, we're not doing that because we've invested hundreds of millions of dollars in existing infrastructure, and the benefits of doing this automatic tuning of controllers are not entirely clear. So we came up with an alternate approach, which is this approach where we said, we're going to replace the role of humans in maintaining the controllers. Instead, we're going to tune a reinforcement learning agent that's going to maintain these controllers. So that was the middle ground that we settled on. And then we spent 6 or 7 years working to make these controllers more efficient, stable, and so on. All right. Now, there are a few problems. As soon as we started thinking about it, a few challenges became very, very obvious. I will describe what reinforcement learning is in just a moment, but think of it as a tool that allows you to take optimal decisions in the face of uncertainty, right? You can leverage observed data to improve operations. You can directly use the data to improve your ability to control a process. If you're using reinforcement learning, you need minimal prior domain knowledge. In other words, you don't need a model. You can, of course, use a model to build a reinforcement learning controller, but even if you don't have a model, the beauty of reinforcement learning is it's going to probe the system and help you design a controller or an agent that's going to control your system. And therefore, you can automatically maintain controllers on a variety of systems. So that's the benefit of reinforcement learning. It's going to probe the system, learn the system, and automatically start controlling it. But the problem is it's going to introduce additional algorithmic complexity. There are auto-tuners that already exist in the industry. For instance, Honeywell, all the major vendors of control software, they have existing auto-tuners. And when you use reinforcement learning, you really have to guarantee stability during and after training. Stability is an absolute minimal requirement when you're designing a controller. If you can't design or guarantee closed-loop stability, then nobody's going to use those tools, right? So we wanted to make sure that reinforcement learning guarantees stability. There are not that many results in the literature on reinforcement learning that is guaranteed to be stable. Sorry, go ahead.
Thank you. One question about, can you give us some example about what are the factors that make the system get out of tune, controllers?
Out of tune?
Yeah. What are the factors to make it?
Do you mean out of tune, out of unstable?
Yeah, because you have to tune it once more. I'm talking about the controllers, that there should be some agents to do that. What are the factors that are making that kind of imbalance?
Oh, I see. Okay, that's a great question. So for instance, are you familiar with simple systems, say first order system, right? So it has you have a certain gain, you have a certain time constant, and you design an optimal controller for that system, right? Often what happens is your gains change. Let's say your production rate changed, and you're pushing more through your process. Then your gain is going to change, right? Or there's fouling in the system, and other things can also change, time constants and so on. So when those variables change, then the controller you designed earlier for a different set of controller parameters are no longer optimal, right? So there are many, many different ways in which gains, time constant. Simple things like if you're in Canada, it can get in some places very, very cold. So your gains in summer are probably going to be different from gains in winter. The heat transfer is going to be different, right? So the processes tend to change quite often. Did anyone here tune a controller on a real plant or real process ever? French, did you? You did. Okay, what was your experience? Was it easy?
I mean, I've done like the guess and check method where you just sweep everything, but you can't do that as well on like a safety critical system. So then you have to actually think.
It's. I mean, even you would think if you use MATLAB and you say you're tuning a PID loop, you would think it's pretty straightforward, right? You know the model, but it's really hard. Even simple loops, it's not that straightforward. So I'll tell you my experience, right? So I was tuning some controllers at a pulp mill, and we go in the morning at 9 a.m. Simple loops. I was very new, fresh out of my PhD, and I told my boss I'll finish it in half an hour. Right? So we go in, and then that process had a time constant of 20 minutes or something like that, right? 15, 20 minutes. So we thought, okay, so we're going to make a few bump tests, step changes, and then we collect the data, find out what the control parameters are, and then it's done, right? 15 minutes, I want 5 times time constant, maybe an hour and a half, my experiment is done, and then I'm done tuning the controller. It took us an entire morning and half of afternoon to tune those controllers, partly because what happened was we started bump test, and then suddenly there's huge disturbance, and then the outputs go haywire. We don't have good data. Then we restart the experiment and so on. Right? It's very hard. I should say it's very hard, but it is not easy to tune even simple controllers, and that's because there's just so many things that we don't fully understand. We're approximating them. We have a much simpler approximation or abstraction of these models that are different from the real system. Did I answer your question? Yeah. Right. So our goal really is to balance automation and scalability of reinforcement learning with control theoretic tools to create efficient and safe improvement. So what I'm going to do is in the next few minutes, it's really simple right now, and we're going to slowly ramp up the complexity of these algorithms. If you don't understand, it's okay. I don't expect everybody to understand everything that I'm saying. If you understand, come to me. I would like to offer you a job. Right? But there are a few takeaway points, right, that I hope you can get by the end of this presentation. All right, and we're going to do this with reinforcement learning. Reinforcement learning has been around for many decades. You've probably seen it or heard about it in many different ways. It's right now it's widely used in a number of different areas. It's used in building games, software for games. It's used even in fine-tuning large language models. It can replace control theory. And there are a lot of parallels between control theory and reinforcement learning. I think these two areas have sort of developed over many decades parallelly, but there are lots of areas of commonality. The idea is if you have an environment or a system You can use an RL algorithm and an RL agent that's going to generate some actions. Those actions result in observations. Observations are then used by the algorithm to generate new actions using what is called a reward. The agent is given a reward function, and its goal really is to maximize that reward as it's trying to perform actions. Okay, so I'll get into reinforcement learning again in just a few minutes, but that's broadly speaking the idea at a high level. Reinforcement learning people have been using reinforcement learning in process systems engineering. There are many papers published recently. I would say one of our papers, I think it's here, it's probably not here, that one over there. That was probably one of the first papers published in PSC with deep reinforcement learning. Although I would credit Professor Jay Lee at University of Southern California for introducing reinforcement learning in PSC. They did not call it reinforcement learning, and I think that was their mistake. They called it approximate dynamic programming. A good friend of mine at Seoul National University, he was instrumental in who worked with Professor Jay Lee. He was instrumental in bringing these ideas to the process systems engineering. Okay, now as I mentioned earlier, the problem with reinforcement learning is that we cannot guarantee stability, and we also want to make sure that it is sample efficient. It's not consuming a lot of data. All of the, or a vast majority of applications of reinforcement learning that you see in computer science are, say, in gaming or in related areas where you have a lot of data you can simulate. For instance, if you want to build a software that plays the game of chess, you can generate lots of data. There is no limit to how much data you can generate. But on the other hand, if you want to use reinforcement learning in real systems, in the process industry, you cannot generate lots and lots of data because generating data costs money. There was a speaker from Stanford who gave a talk at UBC now maybe a couple of years ago who was saying that they do some physics experiments at Stanford. Collecting one data point costs them $1 million. So you can't use a tool like reinforcement learning to generate data from experiments of that type, right? I mean, that's an extreme case, but in many systems engineering problems, generation of data does not come free. You have to be very careful in generating the data, right? So sample efficiency is a problem with reinforcement learning. So I'm going to start with stability, and I'm going to assume that you all know what stability is. So how are we going to guarantee reinforcement learning is stable over all, reinforcement learning is stable over through its, as it goes through its iterations, right? I'm going to divide this into 3 pieces. I'll talk about something called Willem's lemma that allows us to characterize the dynamics of a system using data without having to use an explicit parametric model. And then I'll talk about something called Yula-Kucera parametrization. That's a recipe for characterizing all stabilizing controllers. And finally, learning algorithms. Okay, so we're going to use reinforcement learning. We'll put all of these three things together to come up with a modular setup that really decouples learning from stability. How many of you know any or all of these 3 ideas or tricks? Or have heard of? Did anyone hear about Willem's lemma? No? Okay. Yula-Kucera parametrization. If you've taken a course on classical control theory, you would have heard about Yula-Kucera parametrization. Learning algorithms, I'm going to talk about reinforcement learning. So we'll take our time, and I'll go slowly and try to explain what these are. Hopefully you can take these ideas and use them in your own research or in your projects. Okay. I'm guessing you're all familiar with standard linear time invariant systems. That's a standard state space model. U's are inputs, Y's are outputs, X's are some states. A, B, C are state space matrices. For simplicity, I'm going to assume that inputs and outputs are scalars. A, B, C are unknown, but we can observe U and Y. Okay. simple state space model. A lot of systems in the industry can be locally, at least, defined using this very simple equation. You've all heard of, I'm guessing, impulse response. If you all know what an impulse response is. So if you have a state space model, you can very easily write down expressions for the impulse response. Nth impulse response, Yn, is going to be the product of your state space matrices, C times a to the power of n minus 1 times b. So that's the impulse input, and that is the response. There are a couple of concepts that I'm going to use to describe Wilhelm's lemma. One is controllability. We've probably heard of controllability and observability. Controllability is the ability of us to steer a system to any state of our choice. Okay, so if you can steer our system to, say, some arbitrary state x star using a certain input, if an input exists, so that we can move the system to that x star, then we have a controllable system. And it turns out that the matrix that you see there with the calligraphic C, if that matrix is full ranked, then you have a controllable system. Okay, so that matrix is derived from the state space model. Similarly, there is a complementary concept called observability. We say that a system is observable if given the inputs and the outputs, we can uniquely determine what the underlying state is. In this case, it's x star, and it turns out that if this matrix, defined by capital O, if that matrix is full ranked, then you have an observable state. Now, if you multiply the observability matrix and the controllability matrix, you get this matrix. It is what is called a Henkel matrix. And along these off diagonals, you have the impulse response coefficients of your system. Okay? And Wilhelm's lemma very cleverly makes use of this Henkel matrix to characterize any linear system. Okay, so how does it do that? So if you have an impulse response, the beauty of linear systems is when you scale the input or translate the input, you can do the same with the output without having to recalculate everything. Right? So you have an impulse, and then you can move that impulse and generate more impulse responses very easily. As long as you have that, you can generate all of these. And the span of these data vectors really characterize the input and output combinations, any input and output combinations of a system. Okay, so let me take a pause here and explain what I'm trying to do. So that matrix on the left-hand side, the span of that characterizes every combination of an input and output of a linear system. And that is Wilhelm's lemma. And let me generalize that. If you have a given signal, zt, with capital N data points, we define a Henkel matrix, very similar to the impulse response Henkel matrix that I showed you earlier. And then Wilhelm's lemma essentially states that if you take the Henkel matrix of some inputs and concatenate it with the Henkel matrix of the outputs, the span of that matrix will include every combination of U and Y that you can achieve from a given system. Okay? U bar and Y bar are some new arbitrary data. So if I collected data U and Y, and I can, and the data have to be persistently exciting. That's a very important criteria. And if the data are persistently exciting of a certain order, and I create these Henkel matrices, H U, H Y, then any new set of data, U bar and Y bar, can be written as a linear combination of the input and output Henkel matrices. And that's the core of Wilhelm's lemma. So what we did was we took Wilhelm's lemma, because now if you can do that, you've essentially characterized the dynamics of a linear system, right? Once you have that, you know what the linear system is. So we took that Wilhelm's lemma and modified it slightly to account for, for predicting future outputs. We use what are called nested Hankel matrices. There's a little bit of modification of those Hankel matrices, but it allows us to make predictions on the output. Given any input, we can use these Wilhelm's lemma Hankel matrices to predict what the future is going to be given any input. Right? Now, the central idea here is we did not use an explicit parametric model to make predictions on the output. Right? We've used existing data. As long as the data are persistently exciting of certain order, we can use that data, create these Hankel matrices, and that essentially becomes our model. We use that to make predictions into the future. Yeah.
So I think maybe I misunderstood. What do you mean by persistently exciting?
Persistently exciting. Okay, that's a great question. So let's take a simple example, right? So let's say, are you familiar with ARX models or
Autoregressive?
Autoregressive models, right? So it's in ARX models. The beauty of ARX models is that you can solve for parameters using least squares, right? So when you use least squares, you have to invert a matrix, right? If your system is not persistently exciting, you won't be able to invert the matrix because it's not going to have proper condition number, right? So persistently exciting, what it means, so let's take an extreme example, right? Say you collect data where your input is not changing, output is not changing. There's no real information in the data. You can't use that data to build these Hankel matrices or to estimate the parameters of a model because that data are not informative enough, right? And it turns out that theoretically you can prove for linear systems at least that your data has to have this persistent excitation condition in order to be able to reliably estimate the parameters or characterize the system, right? If it's not persistently exciting, then you won't be able to characterize the system. So that's a condition. Yes.
Why are you assuming a linear system? That, of course, like it's locally linear, but
Right.
if you're trying to find the set of like all possible spaces, isn't it typical that you'll get towards the bounds of nonlinearity when you go towards the edges?
Right. I mean, it's possible. Like, I'm using linear approximations here because it's much easier to explain. But we've extended some of this to. I shouldn't say some of this, but I'll show you how we bring in nonlinearity. But when you're treating nonlinear systems, a lot of the analysis that I'm going to show you sometimes falls apart because it's not easy to prove things to. It's not easy to guarantee stability and so on. Okay. Thank you for all those questions. But it's we're going to be a little slow, but that's okay. I have time until 1:15. Is that right?
Yeah, kind of.
About 1:15. Okay. Yeah. We've only made halfway through my presentation.
How?
But I appreciate
coming because there's another class.
Right, yeah. So 1:15, right? So 1:15, they get to ask questions. Is that right?
1:15 we stop.
We stop. Okay, all right. Okay. So then let's
Come in
go.
a condition.
All right. Okay. Let's go a little faster now. So what Yula-Kucera parametrization? What it says is, if you have a closed loop system. Oops, sorry, there are just too many animations here. Oops. Let me just read the thoughts.
Self-driving slides.
Yeah. Okay, so let's let me get out of the presentation mode. So Yula-Kucera parametrization basically says that if you have a controller, a linear controller, and if you can parameterize it in this way, where you use an approximate model of the process P inside the controller and use a Q in this positive feedback structure, as long as you guarantee that this Q is stable, you can also guarantee that the closed loop system is stable. Okay. That's what Yula-Kucera parametrization is. You're parameterizing the controller with the model of the process and some new parameter Q. As long as you can guarantee that parameter Q is stable, then the entire closed loop system is also going to be stable. So what we did was we figured out a way to guarantee that the Q is stable, even for nonlinear systems. This was a paper published in NeurIPS in 2020, almost shearly stable deep dynamics. We build deep neural networks for Q that are always stable, guaranteed to be stable. Those are nonlinear, by the way. We can use nonlinear Q there, not necessarily linear Q. I know some of this is probably a bit too much to learn in just a few minutes. So we have two ingredients right now, Willem's lemma, and then the Yula-Kucera parametrization to guarantee stability. And final ingredient is reinforcement learning. In reinforcement learning, you have an RL agent that generates actions AT, which the environment generates a reward, and also a state. The agent looks at the reward and updates its actions. Okay, so you go through these loops many times iteratively to maximize a certain reward by identifying a policy, which I'm calling pi. Policies are also called, are basically like controllers. Okay. Now when you put all of this together, you get reinforcement learning over all stable behavior. This is a representation of the data Hankel matrix in Willem's lemma. That's your model, the process P. This is a representation of all stable Qs, and this is your industrial process. And when you put all of these things together, you will be able to separate learning from stability, and therefore you have a closed loop stable reinforcement learning algorithm. We've tried this on a pilot scale plant. That's Nathan Lawrence. He's currently at Berkeley as a postdoc. What you see there is a pilot scale plant that was set up for us at Honeywell. University of British Columbia is over here. Nathan used to drive to Honeywell in North Vancouver and perform these experiments. He did some of these experiments during the pandemic. That's why he's wearing a mask. And as expected, we found that the closed-loop system was always stable, and then the system was also tracking the set points really well. I'll give you 5 minutes. I won't be able to finish my entire presentation, but I'll give you at a very high level some of the ideas. So when we finished that, we did all these experiments on a real system, but then we wondered, okay, Honeywell already has these auto-tuners. Why don't we compare what we did with Honeywell auto-tuners? And we very quickly realized, I'll just show you this this picture here, this table. This is a paper that was published in 2024, Control Engineering Practice. Deep RL is our algorithm. AccuTune is a Honeywell auto-tuner. SIMC is Skogistad internal model control. He published a paper, I think, with the title "The Best Tuning Parameters for PID" or something like that. And on all of these different criteria that we use, deep reinforcement learning performed much better than other controllers, except in one criteria, which is time required for tuning. Auto-tuners would tune a controller in about 5 minutes. Deep reinforcement learning took 40 or 50 minutes, right? And that's not acceptable because you're losing production in a live setting. So that really spawned a lot of research from my group on sample efficiency. How do we improve sample efficiency? Naturally, if you can, if you provide reinforcement learning with a model, it's going to do far better, right? All of our experiments were done without a prior model. But having a model is not always easy. There are lots of reasons why you may not have it. High fidelity model, right? So we then thought, okay, maybe there's some middle ground where you don't give it a complete high fidelity model. Instead, you give it something in between, some partial information, maybe a model structure, maybe some parameters you know. And that led to a lot of work on improving sample efficiency. One of those algorithms is what is called meta reinforcement learning. I don't know if anybody here has heard about meta reinforcement learning. The idea there is if you have a system, you assume all possible models for the system, you train your RL agent offline, and then you take it live. When you take it live, it quickly figures out what system you have among all the systems that you trained it on and starts controlling it much better. So this meta reinforcement learning is is a lot more sample efficient than the vanilla off-the-shelf reinforcement learning algorithm. We've then tested it on a wide range of processes. It helps you in adapting to changing process conditions, and it performs, especially when your process conditions are changing, it performs much better. Okay, I'm going to show you, I just want to wrap up in 2 minutes, then you have 5 minutes to ask me questions. In addition to that, meta reinforcement learning, one of my students, PhD students, he's just wrapping up his PhD. He did some really interesting work on incorporating prior information into reinforcement learning algorithm. I'll just explain what is here. This is a very simple pendulum example with that reward function. If you give this reward function, off-the-shelf vanilla reinforcement learning would do really well. But if you change the objective function, the reward function, remove this 10, then it's not going to be able to control the pendulum. This is our approach with partial information. We are able to control the pendulum with limited or partial information. He then extended those ideas to develop what are called end-to-end learning algorithms. There, the idea is in reinforcement learning, you typically approximate the policy using a neural network. In deep reinforcement learning, that's the common approach. What we have done is we have embedded control and model structures into the neural network and trained all of them together at the same time for end-to-end learning. Instead of having to tune the controller, you treat that as the last layer of the neural network and tune it. The problem is when you have MPC or LQR, they're not differentiable. You can't differentiate them. So when you're training networks, you have to go through a forward pass and a backward pass. But that's not possible if you have a MPC or LQR. My student was able to overcome that using fixed point iterations. Okay, so that's probably not easy to understand, but the idea is to embed the control structure into your neural network and train everything at the same time. Okay, so that leads to much better results from reinforcement learning. This is a very simple simulation of a rocket landing. Starting from different initial points. He does not provide reinforcement learning the entire model of the rocket. He only gives it the structure of the model. Parameters are missing. Some maybe 1 or 2 parameters are given, but a lot of parameters are missing, and you see that it works really well and lands the rocket on its landing pad. Right. So I'll show this last example. Again, this is our proposed approach where the robot is able to track a previously determined path really well with partial information given to it. We don't give it the entire model, just a few aspects of the model. On the right-hand side is a robot that's not able to track. Okay. If you use soft actor critique, is a very popular reinforcement learning algorithm. Okay, I'm not sure. It's not moving on the right hand side. I'm not sure why. Okay, there. All right. So 112. I know there's probably a class after this. I think the big takeaway for all of you here is reinforcement learning is a great tool if you want to maintain your controllers automatically without that human involvement. But the challenge is you have to guarantee stability and you have to guarantee sample efficiency. Those two are critical. Because of those two reasons, I think reinforcement learning is not yet ready for wide adoption in the process industries. But if we can fix stability, which we have done to a large extent for linear systems, and if we can also achieve good sample efficiency, then there are benefits to using reinforcement learning. Okay. All right, I'm going to pause there, and I'm happy to take any questions.
Thank you very much. Please.
So you had the slide where you had proposed the deep learning controller plus the RL, but then the compromise was regular controller plus RL. What are the performance differences between those two by going with the compromise? And I guess why would that intuitively be the case if it's assumed to be a linear plant anyway? Is a linear controller not optimal?
I mean, controllers are optimal if you know the model, right? If you know the model exactly, then you can design an optimal controller. In fact, I think a few months ago, Yula-Kucera, I don't know if you know him, he's the head of AI research at Facebook. He tweeted, forget about RL, just use MPC, right?
Yeah.
Ben Recht is another person. He's at Berkeley. He says the same thing, right? So if you have model, use model-based RL. Model-based RL is far better, far superior to model-free RL. But what the challenge is, models are not, especially in the context in which we operate, process systems engineering, models are not easy. If you're dealing with a robot, right, where the physics are well defined, and there are uncertainties, but the physics are very well defined, so you can get a more or less accurate model, perhaps. But if it's an industrial system where we don't fully understand the underlying physics or the chemistry, and there's just a lot of uncertainty, we don't have good models. Right? So when you don't have good models, I think you'll benefit from using reinforcement learning. If you have a model, you can use model-based RL or MPC. You're probably going to be good. You don't need RL. Right? So yeah, if you have a model, then a controller that's optimal with respect to that model will do really well, much better than anything you can do with reinforcement learning.
Question?
Yeah, I have additional question on that, I guess. So earlier you said you have a lot of data. So why not learn the model from the data, some kind of systematic information from there,
right,
and then use it?
You can, right? I mean, that's always an option. What we're trying to do is eliminate the involvement of humans in maintaining these controllers and designing those controllers, right? And that's the advantage I think you get by using reinforcement learning. Reinforcement learning has this approach of exploration and exploitation. Exploration is when it's trying to probe the system, generate data, and exploitation is when it's trying to use that data to control the system, right? So you can do that automatically. It comes with that inbuilt exploration and exploitation approach, which is lacking in standard classical controllers. There is adaptive control. There's a lot of research on adaptive control. People have done that for many years.
So I guess in the interest of time, we can conclude here. Please join me in the thank you.